Hello. Good morning, everyone. Thank you for joining this seminar. We are honored to have Dr. Avinash Unnikrishnan for the Warren presentation today. Dr. Unnikrishnan is an associate professor at Portland State University in the Department of Civil and Environmental Engineering. Avi has a master's degree in civil engineering from Vanderbilt University and a PhD in civil engineering from the University of Texas at Austin. His work is primarily on transportation networks and optimization of transportation networks with application in traffic and freight network. Avi's work has been funded by National Science Foundation by multiple awards and multiple DOTs, including Texas, Oregon, and West Virginia. Avi is a winner of a prestigious Burggraf Award by Transportation Research Board for his work on modeling parking search behavior of drivers in uncertain network. Without further delay, Avi.
Thank you, Ali. For those of you who are looking at my last name and trying to pronounce it, I go by Avi, so you can all call me Avi. Okay. A lot more easier. Okay. Before I start my presentation, I'd like to thank all of you for hosting me and giving me this opportunity. Okay. So the topic of my presentation is a three-level location inventory problem with correlated demand. Okay. So this is the overview of my presentation. I'll first provide the background and the context of my research. I'll then present the mathematical modeling formulation, the solution algorithm, some computational analysis, and directions for future research. Okay. First, a little bit of background and context. Supply chain networks pretty much form the backbone and foundation of almost all the industries we see around here. Now, given the competitive nature of today's market, due to factors like globalization, access to relatively inexpensive tracking and monitoring technologies, freight agents and freight managers are now looking to optimize pretty much each and every aspect of their supply chain. An optimized supply chain leads to reduction in cost, which leads to higher profit and greater competitiveness. Okay. Now, in this research, we are going to focus on what is called as a three-level supply chain. Essentially, there are factories which manufacture goods, okay, hopefully less polluting factories, okay, which supplies goods to warehouses, which stores inventories, okay, which then supplies goods to customers or retailers. They are like Walmart, Lowe's, Target. Those are the customers and retailers. Okay. This is a more abstract view of the supply chain. Again, we have factories, we have warehouses, and then we have the customers and retailers. Now, in this research, we are going to focus on a single commodity supply chain. That is, we are going to focus on a supply chain where only one commodity is transported from factories to customers. That is not a big restriction of the research I did. The models I presented and the algorithms can be easily extended to multiple commodities. But for the sake of ease of notation, we are going to stick with a single commodity. The second main assumption made in this work is single sourcing. So what is single sourcing? Single sourcing means that each customer is assigned to one warehouse and one warehouse only, and each warehouse receives goods from one particular plant only. If you look at the freight literature, there's a lot of debate between single sourcing versus multiple sourcing, advantages and disadvantages. But you'll see that a majority of the literature is still dominated by single sourcing. It has its own advantages, especially because customers tend to develop relationships with warehouse managers, and it's far more easier to take care of some of the operational details when you're dealing with the same person for 10, 15, 20 years. Okay? Now, I wasn't sure about the freight background of the audience, so I'm going to give a little bit of background on supply chain decision making. Okay? Supply chain decision making can be classified into three categories. There is strategic, there is tactical, and then there is operational. In strategic decision making, you have a bunch of potential sites for locating plants. You have a bunch of potential sites for locating warehouse, and you have the customer locations, and you know the demand. Okay? The goal here is to pick from these sites ideal sites to locate plants, pick ideal sites to locate warehouses, and then link customers to warehouses, and then link warehouse to plants. Okay? The more plants you locate, obviously the location cost increases and the transportation cost decreases. So there is a little bit of trade-off here. The objective in strategic decision making is to locate facilities to minimize the location cost and minimize the transportation costs. Okay? If you look at the literature, there is tons of papers on strategic facility location, different variants, single sourcing, multiple sourcing, deterministic, economies of scale. Does the warehouse or the plant have capacity? Does it not have capacity? I mean, you'll find at least like 10,000 papers. One of my personal favorite paper is the Lagrangian heuristics for location problems by J.E. Beasley, published in 1993. This gives a very, very good introduction to the topic and presents a lot of cool solution methodologies. It's not the latest, but it's just my favorite. Okay. Yeah. The next level of decision making is tactical decision making. Essentially, once you know where the warehouses are located, you manage the inventories at those facilities. This slide is like inventory management 101. Okay, so at each warehouse you have inventories or stocks which are decreasing over time. Okay, it decreases because they are constantly supplying to customers. Now, as the stock decreases and hits what is called as a reorder point, the manager of the warehouse places an order. Okay. It takes a little bit of time for the plant to process the order and deliver the goods. The stocks continuously keeps on decreasing. The time it takes for the plant to deliver the goods is called as the lead time, which is this time. Once the stocks reach the warehouse, again it jumps up, okay, and the process continues. Now, when the demand is uncertain, okay, warehouse managers often carry what is called as a safety stock to account for sudden spikes in demand. For example, there could be a scenario where you have only 10 barrels of potato in your warehouse, and all of a sudden a restaurant owner calls you up and said, I need 20 barrels by tomorrow. And if they can only deliver it before day after tomorrow, you're actually losing that customer. Okay, and they want to prevent that, so they have a little bit of what is called as a safety stock. Again, the goal in inventory management or in tactical is to minimize this total inventory cost, or rather the holding costs, the safety stock costs, and the cost of associated with placing orders. There's a little bit of cost associating each time you place the order. Okay, and again, there is tons of literature out there. There is this latest book by Axeter, which is in 2008, which gives a great overview. One of my personal favorite is this book by Hadley and Witten. It is written in the 60s, but I still like this book, okay, which provides a good overview of the tactical side. The final level of decision making is operational. Okay, essentially in operational, you have the demands. You need to supply to locations A, B, C, and D. Okay, you need to supply it by a specific point in time. You have 3 trucks and 5 drivers. You manage the crew. You manage the trucks so that the deliveries are made. Okay, this presentation will not deal with the operational side at all. We are primarily dealing with the strategic facility location and the inventory management side of things. Okay, now, when you're looking at strategic, tactical, and operational decisions, they vary a lot in their time frame of application. Strategic is more facility location decisions, right? They are taken with 10 to 30 years in mind. Okay, it's very difficult if you decide, okay, I'm going to set up a facility in Minneapolis and Chicago, and all of a sudden you cannot just decide, okay, I'm going to close that facility and move it over to Portland or San Francisco and stuff like that. These are normally very long-term decisions, so you have a longer time frame in mind, often 30 years or 20 years. Okay. And in today's climate, it's also a politically sensitive location decision, where you locate, where you move, so you need to be really careful. Tactical decisions are mainly taken with almost like a 1 year or a 2 year. You're managing inventory, so you have a time frame of a year or 2 to take those decisions and apply those decisions. Whereas operational, these truck routing decisions are taken almost on a daily or a weekly or a monthly basis, depending upon the size of your operation. Okay. Traditionally, these have been done sequentially. You first do the strategic facility location. You do it separately. Once you know where the facilities are, then you start dealing with the inventories. And once you know where how the inventories are managed, then you start dealing with the truck routing on a daily, annual basis. So they have been studied separately. In the early part of the previous decade, several researchers, mainly Mark Daskin and his student Max Shen and several of his students, and Pablo Miranda and Rodrigo Garrido, okay, they showed that there is value in jointly deciding the location of the facilities and optimizing the inventories. Okay? This is because in some of these high-valued but perishable goods, like for example blood banks, okay, or perishable organic goods, okay, the cost of managing the inventories started creeping up. And across a period of time, it started almost equaling or becoming a significant percentage of the facility location cost in itself. Generally, you think, yeah, locating the plants is the most expensive thing. Inventory should be cheaper. But when you have this sensitive, high-value target, the inventory management costs also started creeping up. Okay? And with e-commerce, Amazon, all of these companies exploding, inventory management became as critical as locating facilities. Okay. So essentially they showed that rather than doing them sequentially, in certain cases it's better, or actually you can get a lot of value by jointly doing it. This led to what is called as joint inventory location problems. Okay, where you locate the warehouses, the plants, decide which customers are going to be served by which plants and which warehouse, okay, and we optimize inventory decisions and safety stocks also. There have been around 20 to 30 papers in the last decade on this topic with several models and solution algorithms, the most popular of which was the Lagrangian relaxation-based algorithm. Okay? Now, next I'll present the model formulation I studied, some of the assumptions I made, and how my model is different from some of the past works. Okay? Again, a little bit of context on the problem I study. One of the main difference of this work from the previous work is that I looked at a 3-level facility problem where you try to locate plants, you try to locate warehouses, and there are customers. Almost all of the work which has been done previously in the joint location inventory framework looked at 2 levels. For them, they assume that the plant location is known and fixed, whereas in my case, the plant location was a decision variable. You can also change the location of plants. Okay? This added an additional layer of complexity to the problem. Okay? So we have a bunch of potential sites for locating plants, a bunch of potential sites for locating warehouses. There is fixed cost associated with each located facility, and each of these warehouses have capacities too. Okay? Now we have retailers or customers over here. Similar to past work, we assume that the retailer demands are uncertain with known means and variances. Okay? But the big difference between my work and past work is I assume that the retailer demands are correlated. Previously, almost all of the work, I wouldn't say almost all of the work, I'd say all the work assumed the demands are independent, which is a very strong assumption, because if you look at customer demand, depending on season, depending on space, depending on what time you're looking at, there will be a lot of correlations among the demand for particular type of goods. Okay? So I assume that the retailer demands are correlated, and I'll show later that this actually adds significantly to the complexity of the problem. With respect to the inventory decisions, it's pretty much the same. You try to decide, once you know which facilities are located, you try to decide the optimal order quantity, okay? How much order you place each time, the reorder point, the time when or at what stock level will you place the next order, and the safety stock needed at each warehouse. Okay? And then we also make allocation decisions. That is, we assign each customer to one particular warehouse and each warehouse to one specific plant. Okay? In that context, yeah, it's similar. Okay. I won't go into the details of the objective function and the variables, okay? But I'll provide an overview. The objective is, in general, is to minimize costs. Okay? That's the objective here. We have 6 of these terms. Okay? The first two terms essentially correspond to locating the cost of locating plants and the cost of locating warehouses and the connection cost between customers and warehouses. Okay? The assumption here is that with each location there is a fixed cost which varies depending upon the location. It may be like, I don't know, $20 million to locate one facility in Minneapolis and $50 million to locate one facility in Chicago. Then the total cost will be 20 plus 50. It's one-time fixed cost. Okay? Then we have the transportation costs. The transportation cost is between the cost of transporting the goods from the plant locations to the warehouses. You have that level of transportation. And the transportation cost of transporting goods from the warehouses to the customer. So you have two levels of transportation here. Okay? And in the end, you have what is called as the inventory cost. So this is the inventory ordering cost. I'm not going into the derivation of each of these terms. This is the inventory ordering cost. That is, each time you place an order, you have a specific cost. And this is the inventory holding cost. Okay? Now, there are three sets of constraints. Okay? The first set of constraint is what I call as a locational constraint. Okay? Essentially, these constraints enforce that every customer is only assigned to a plant which is opened, or to a warehouse which is open. We don't want to assign customers to a warehouse which is not open, right? Same way, every warehouse is assigned to a plant which is open. Okay, that's what these two set of constraints does. And then we have the single sourcing constraint. It ensures that each customer is assigned to only one warehouse, and each warehouse is only assigned to one plant. Okay? And then we have the capacity constraint, which essentially ensures that the amount of goods flowing through a warehouse is less than or equal to what that warehouse can handle. Okay? And last one, these are the definitional constraints for each of these variables. Essentially, they are 0-1 variables because the decisions we are making are of the type of, do we locate a facility or not? If we locate a facility at a location, then it takes 1. If not, it's 0. Is there a connection between a particular customer and a warehouse? If there is a connection, it's 1. Otherwise, it's 0. Okay, so we are enforcing this 0-1 constraint. Okay? So this is how the first nonlinear formulation which I developed looks like. Okay? So these are the constraints again, and this is the objective function. Okay? Now, remember I said that one of the assumptions I made is that the demands of retailers are correlated. Okay? That adds significantly to this nonlinear term. If you, for example, if there are 100 retailers, and if they are independent, there will only be 100 of these terms, whereas now there will be at least 100 square because of the correlations between all of them, and that just throws the nonlinearity into a whole new spectrum. Okay? And because of that, we couldn't use the traditional solution, the traditional popular solution methodology, which is Lagrangian relaxation, to solve this model. Okay? Now, this is a highly nonlinear integer problem. Okay? In general, in optimization, linear is good, nonlinear is not so good, integer is not so good, integer nonlinear is really not so good. Okay? That's how it is, right? People from the industrial engineering department might not like my summary, but that's generally what it is, right? So, if you look at here, we have the integer, okay, because we are forcing this to be either take value 0 or 1. And then we have a nonlinear term here, which is where we multiply 2 of these decision variables. And then we have one more nonlinear term here, where we multiply 3 of these decision variables. And then we have the square root term, which adds to a whole new level of nonlinearity. Okay? So this problem is hard to solve. Okay? And to solve this, you often have to use these global optimization solvers like Baron. Okay? And as I'll show in the computational results, these solvers can handle only reasonably small size of problems, and we need something which can handle moderately large size problems. Okay? Now, so what we are trying to do is, the next step is to convert this nonlinear integer problems into something which has nicer, okay, but delivers the same solution. Okay? So the first step is we look at this nonlinearity. We look at this particular nonlinearity. Okay? Remember, this x and y's are 0, 1 variables. So this product can take only one value. It can take either 0 or it can take 1, because both of these variables, x's and y's, can take either 0 or 1. Okay? So we introduce a new variable m, which takes 1 when both x and y is 1. And in every other case, when either x is 0 or y is 0 or both are 0, it will take value 0. Okay? So we introduce this new variable. Now, in Hanif Sherali at Virginia Tech developed this technique for linearizing, where we replace xij, yj with m, and to enforce that, you add these constraints. We remove the nonlinearity. Unfortunately, we increase the problem size significantly because we are adding more and more constraints to the problem, which makes it again difficult to solve. What we developed in this research is a new method, okay? A new way of linearizing. It's more efficient than this. It's not great, but it definitely is more efficient than this, because it uses lesser number of constraints. In general, it reduces the number of constraints by like 30%. Okay? Now, so this is the next formulation. I have replaced this by m. We have the original set of constraints here, okay? And we have added new constraints. Yes, one source of nonlinearity is gone at the expense of a new set of constraints. That's the trade-off. Okay, which is not, where the number of, you're adding a reasonable amount of constraint, but not as high as the standard techniques. Okay, so now we have this, but we still have this square root problem here. That is a source of nonlinearity here. Okay, now what we did to take care of that square root problem is we actually took the terms from the objective function and introduced them as constraints. We have the new constraints, which is the m-related constraints and the original constraints here, okay? And we introduce them into these constraints. And remember, this x is again a 0, 1 problem. It's a 0, 1 variable. It takes value 0 or it takes value 1, okay? So when x takes value 0 and x takes value 1, x square also takes value 0 and 1, okay? X square can only take value 0 and 1. So we replace this xij by xij square. Okay. Now, why convert this linear to another nonlinear term? Okay. The reason why we did that was, now the objective function is integer linear. All of these constraints are integer linear. Okay. We can actually show that these set of constraints are actually convex functions. Okay. By making this transformation. Okay. So this is integer linear, this is integer linear, and this is a convex function. This nonlinear formulation actually has what is called as convex mixed integer nonlinear program. Okay? Now this convex mixed integer nonlinear program actually has some nice properties, okay, compared to a traditional integer nonlinear program. There are some efficient cutting plane algorithms in standard solvers like CPLEX, you know, and efficient, and you can also develop, it also opens up the potential for using customized algorithms, okay? And one particular algorithm I used is what is called as outer approximation, and there is a reason why I chose outer approximation, which I'll explain now, okay? Outer approximation was developed by Duran and Grossman at Carnegie Mellon University, okay, at 1986, and further refined by Roger Fletcher and Sven Leifer. I think they are both at, or at least Sven Leifer is at the Argonne National Lab in Chicago right now, okay, and these are the two classic papers in outer approximation, okay. Outer approximation is shown or is proven to guarantee or deliver globally optimal solutions for convex mixed integer nonlinear programs. Okay? There is this paper by Pierre Bonamy and a host of other authors which actually show that. Okay? And the reason and the way outer approximation works is, in a mixed integer nonlinear program, you have two complexities. You have the nonlinearity and you have the integrality, and they're both interacting with each other, and that is creating the problem. What outer approximation does, it separates out the integer part and it's from the nonlinear part, okay, and attacks each one of them separately. Okay? Essentially, it separates the solution methodology into a nonlinear subproblem and a mixed integer linear master problem. So you fix the integer variables, okay, and you solve the resulting nonlinear program, okay, and using the solution of the nonlinear program, you actually do a first order approximation of the nonlinear constraints, make it linear, and we solve the resulting mixed integer nonlinear program. So you go, you iterate these several times until you arrive at the optimal solution. And if the problem has a convex mixed integer nonlinear program, it is guaranteed to deliver the optimal solution. Okay? That's one particular reason why we use the outer approximation framework. Okay? The second main reason is that the bottleneck in outer approximation is solving this nonlinear program. Often when you apply outer approximation to solve convex mixed integer nonlinear programs, the bottleneck or the time which takes the most is this nonlinear part. Okay? In our specific case, we showed that we really don't need to solve the nonlinear program or use any algorithm. We showed that using this analytical relationship, we can instantly get the solution of the nonlinear program. So we have actually removed a big part of the bottleneck. Okay? So we need to solve the mixed integer nonlinear program, and the nonlinear subproblem will have this form. The solution to the nonlinear subproblem will have this form, which a computer can do it like within less than a millisecond, right? So the big bottleneck is removed, and that's one of the main reasons why we chose this outer approximation based solution method, because we have removed the bottleneck. We also did some tweaking to the outer approximation to better fit the existing model, and I'm not presenting that here. Those details are available in the paper. Okay? Now, regarding the computational analysis. So since I presented a lot of formulation, this is just a summary. Okay? First, we have the original nonlinear formulation. Okay? We had the original nonlinear formulation. We solved it using a global optimization solver. There's this one called as Baron, which is a very good industry standard global optimization solver. Then we transformed it into a convex mixed integer nonlinear program, which we solved using a CPLEX solver, okay, which again is the industry standards. Okay, and of course they made it available for free for academics. That helps too. Yeah. And then we implemented our own outer approximations algorithm where the master problem was solved using CPLEX. Okay, now we have all of these three were implemented using the same software platform, and the testing was done on the same computer. What we did was we generated random instances of the problem. And we found that as the problem size varies, okay, for problem size 1 and 2, you can see that, yeah, this is 12 seconds, and OA takes only 0.5 seconds, whereas the CPLEX solver takes like 0.8 seconds. But the minute the problem size jumps a little bit more, you can see that this takes more than 1,000 seconds, whereas the outer approximation was dealing with it in like less than 23 seconds. Okay? That's a huge. And actually, it's not just 1,000 seconds, we ran it for a day. Okay? And in general, we found that this was nowhere close to getting an optimal solution, whereas the CPLEX for the conic, it was getting there, but not quite as fast as we would like it to. And all the results, this is not just one test instances. We generated around 20 random instances and tested it 20 times, and then we averaged it. Okay? And in the paper, we have the min and max and median and all the nice statistics, and pretty much OA dominated in every of the metric. Okay? Then we looked at the value of capturing correlation. Like, for example, as I told, a lot of the research until now assumed that the demands are independent. Okay? we found that correlation actually led to completely different supply chain structure itself. The location of the plant differed, the location of the warehouses differed, the connections from the customers to the warehouses also changed a lot. Okay? And then we took the solution where we assumed that the customer demands are independent and tested it in the case where the customer demands are correlated, and we looked at the savings, and we found that in general you get a lot of savings, up to 12%, and the savings increased, started increasing when you're at a correlation factor of 2.2, and then it remained almost stable after that. So there is a lot of value you get in capturing these correlations. Remember, when you're accounting for correlations, you are solving a significantly tougher problem. So we need to show that it is worth solving this tougher problem, which is what this is showing. Okay. In general, the inventory cost starts diminishing, decreased with demand correlation. Okay, and the reason being that when you have demand correlations, warehouses can account for these demand correlations in creating these safety stocks, because they know that, if you know the correlation patterns, when one goes up, the other is also going to go up, or one goes down, the other is going to go up. You know that relationship, and then you can use that to actually determine the safety stock. So the inventory cost actually decreases, and this can get significant when you're dealing with inventories like blood banks. Okay. And then we looked at the computational time. As you can see, and for almost all the instances, as you go from PB1 to PB10, the problem sizes increase significantly. Okay, you can still see that outer approximation delivers the optimal solution within 140 seconds, whereas both Barron and the regular conic pretty much stopped here. Okay, at PB2. And we also found that the OA runtimes was stable across correlation coefficient. That is, as the correlation increases, the runtimes were a little bit stable. Okay. Some of the future research directions. So from an algorithmic point of view, as I said earlier, we have the nonlinear subproblem, which you're solving analytically. That removes a big bottleneck. But right now we are targeting the master problem. Can we do something to solve this master problem more efficiently? So when you see that 140 seconds, almost like 139.5 seconds of it is solving the master problem now, repeatedly. Okay, so can we do something to reduce the computational time of the master problem? That is a focus of my research. Another research direction which I'm currently interested in is reverse supply chain. Nowadays, with Amazon and people returning a lot of stuff, buying and returning, supply chain doesn't go in one direction. The freight goes in the other direction too. You buy a lot of stuff from Amazon and you return it, a lot of stuff too, right? That's one aspect. There is also, there's a lot of emphasis on green supply chain, recycling, all of this kind of stuff, and so there is a forward movement and a backward movement, okay? And actually, I started getting interested in this topic like 5 years ago, because I wanted to work a little bit on disaster relief operations, where you have relief traveling one way and people traveling the other way from disaster zones. Okay, my PhD was not on supply chain. My PhD was on regular traffic networks. But around the time I finished my PhD, Hurricane Irene happened, and there was a lot of interest on moving goods and optimally planning goods, and I started getting interested in this, which led me, and I meandered my way into into an inventory supply chain problem. And now I want to go back to the reverse supply chain and reliefs. And the big difference being that I want to work on problem settings where we can open and close facilities. Whereas in relief settings, the facility location is temporary, right? It's not like you're establishing a relief center and it's going to be there for the rest of its life, right? And also, when budget is restricted, sometimes on day 1 and day 2, you want to open one center here, and then day 3, move everybody to another operation. Okay, so that is one area I'm interested in, and already have one paper in this context in the closed loop supply chain, but that is in the context of industry and not in terms of reverse supply chain. And currently, from the plant point of view, we assume that when an order comes, the plant can just produce whatever you want, which is unrealistic. Okay? Plants also have worker hour constraints. Plants also have transportation constraints. Okay? And also, in general, in supply chain, the assumption is, okay, there is this one central authority which controls the entire supply chain, and whatever he or she says, everybody will obey perfectly. You know, and that's how most of these optimization models are. But in general, there is a lot of behavioral issues in freight, right? Truck drivers have their own way of operation. Inventory managers have their own way of doing things, and sometimes telling all of them to behave the same way is sort of unrealistic. So how do we actually incorporate behavioral constraints into these models? Okay. With that, I'd like to acknowledge my student, Mehrdad, who's now a postdoctor at the University of Florida, and an industrial engineering student, Ehsan, who works for Mylan. Unfortunately, Mylan is in the news for not so good reasons now. You know. And then we have Steve, my collaborator at University of Texas at Austin, who was a collaborator on this topic. All this research, I mean, this presentation was based on this paper, which is published in Transportation Research Part B. And I'd also like to acknowledge the National Science Foundation for funding this research. The original research was funded through this grant. The Directions from Future Research is funded from this latest grant. Thank you. That's all I have.
Thank you very much for the excellent presentation and great timing. We have a lot of time for questions.
Yes.
So you talked about going from the nonlinear problem to the linear problem. My understanding is that I assume that when you talk about the difficulties of the nonlinear problem, you're particularly referring to non-uniqueness in the solution. First of all, is that correct? Is that what worries you the most of a nonlinear optimization problem?
Definitely. I mean, definitely there is the non-uniqueness aspect of it, and in general, even the solution time in itself, right? I mean, when you have this nonlinearity and when you want to enforce that the solution should have a 0-1 constraint, like you cannot locate half a plant, or you cannot locate half a customer to half a warehouse, right? You need one customer to one warehouse. That just makes the solution space very, very difficult. Yeah.
And for the non-uniqueness part, the way you alleviate it is by putting constraints, essentially that automatically gets rid of some solutions. So is the presence of constraints, of additional constraints, does it automatically allow you to, out of the pool of solutions, to discard some, so that you end up converging on a unique optimum? Do they play that role?
I do not. The algorithms developed converges to a global optimum. There is no guarantee that it's unique. Okay, the uniqueness part isn't guaranteed. All that is guaranteed is that it converges to a global optimal. With respect to the guarantees, I use sort of like the mathematician's way of proving, where if you want to prove something, convert it to something which has already been proved. You know, so what we did is we transformed it into the convex mixed integer nonlinear program. There are standard proofs available which shows that converges to a global optimal if you use OA. That's sort of the technique used. And in a way, yes, writing the constraints in such a way ensures that the solution space has a specific structure which ensures that the algorithm will converge to a global optimal. Not necessarily unique. There could be like 10 globally optimal solutions, but the objective function will be the same, but it will be a globally optimal solution. Okay. Thank you. Yes.
I was just wondering about your, like in terms of the travel part of it, or the transport. Are you doing like shortest path, or do you consider travel time, fuel, like, you know, is there a lot of congestion on this route? Maybe a longer path would actually save you money in the short term?
That's where the operational aspects where we do the vehicle routing comes into play. This is more at the planning level where we abstract a little bit. For example, when you're taking a location decision, generally in the freight industry, what they try to do is they try to come up with a per mile cost, okay? Depending upon the type of transport you do. If you're doing a truckload transport where you're transporting one truckload each time, it's often, depending upon your goods, the cost which comes up is around like 1.6 to 2 miles per, $1.6 to $2.2 per mile. So use a unit cost for transportation. When you actually get down to the vehicle routing level, which is, okay, once you know the facilities are here, once you know these customers are here and they have to be delivered this amount of demand, that's when we take into account stuff like reliability or deadlines, all of those kind of things. This is more at a little bit higher level where we assume, okay, we know it takes 30 miles to go from this warehouse to this warehouse. On an average, it costs per truckload $2.3 per mile or something of that order. It's done at that level. The detailed vehicle routing will be the next step, which I have not taken into account in this model. Okay.
Other questions?
Looking at your stochastic constraints for your shops, the demand points, it looks like your cost is essentially proportional to a standard deviation type of calculation.
Yeah.
But that doesn't incorporate what seems to me to be important given your different time scales for the different of your 3 layers and the different time scales that you highlighted. Shops, for example, come and go in a 30-year period. So each shop would have a probability of existing or not existing into the future. And I don't see how you could incorporate that into your formulation. There is a lot of work in incorporating disruptions in location into joint inventory location problems. That throws an additional layer of complexity. I agree with you that yes, definitely when you're looking at this 20-year time scale, there is a possibility of a shop not existing or moving. At this point in time, we are not taking into account that factor in joint inventory location problem. That would be definitely an additional layer which we would like to incorporate. Yeah.
Just to kind of follow up on this question, my understanding you have a total cost over the entire service life.
Yeah.
But on the other hand, the cost may vary over time. So, for example, even like setting up a factory, you might have to consider higher startup cost versus low operation, or lower startup cost versus high operation cost.
Yeah.
And well, first of all, how you account for those changes, and the second is, it might be a good idea, in addition to overall cost, to get limits on the yearly cost, because some enterprises cannot afford like higher cost per year, so on certain years.
Yeah, actually, in this work, in the objective function, we take this overall cost and we annualize it.
I see.
Okay, so we are looking at an annual. So we have this facility location cost, which is annualized, just like we do the mortgage and stuff like that. So and we try to we take this 1 year period as we convert all cost in terms of the current cost year, and that's the way we do it. But that does give rise to the possibility, as you said, of a lot of uncertainty in costs as well, because we really don't know it's very difficult to predict what a facility location cost, or especially the operational cost in the future is very, very difficult to predict. Yes, that definitely is an additional layer of complexity. But if you look at the industry right now, and they generally, and the state of the art in terms of research, generally they don't worry too much about this variation in cost in 20, 30 years. They try to come up with a good estimate of how much it will cost, and then they'll annualize it. But definitely that is a weakness.
when people do make those decisions.
Well, the industry which I'm dealing with, they're worried only about the next quarter. They don't worry about
exactly.
4 years.
Yeah, yeah, yeah.
Other questions?
So when you find the solution it have the integer variable, and so your cost function will kind of jump between the value of the integer. So how could you account when you do the convex optimization and you draw up the smooth surface solution into the integer solution one?
Okay. In a convex mixed integer nonlinear program, a convex mixed integer nonlinear program is a nonlinear integer program which is convex when you relax the integrality constraints. That's the definition of it. Okay, and in terms of the solution methodology, how the outer approximation works is it decomposes everything into this master problem and sub problem. Okay, the nonlinear part is solved separately. You fix the integer part, okay, and then solve the nonlinear problem, and then you take the and then take the nonlinear solution, and then you linearize, do a first order approximation of the nonlinearity, and solve the integer problem separately. So you have this integer solution and the nonlinear solution, and this communicates with each other. Okay, so that's how we ensure that the final solution has the integrality property, because it's done separately. Okay, but otherwise your point is well noted. Solving nonlinear as well as integer problem, coming up with one algorithm to solve it is very, very tough. And that's why outer approximation works very well in this case, because it's able to decompose it, separate out into the integer part as well as the nonlinear part, and tackle each one of them separately. Okay.
And one more question. When you do your new method to reduce the variable space,
yeah.
What will be the trade-off when we have less variable? Will it affect our result?
In general, as the number of constraints decreases, the solution time should decrease. Okay. Off the top, I don't remember off the top of my head how much it reduced when we did this transformation. But there was around, I do remember, around 25 to 30% reduction in computational, in the number of constraints. In general, it should lead to savings in computational time. I'm just not able to recall it right now. Yeah.
Thank you for your talk. I had a question about how do you evaluate the accuracy of this? Is there data out there that you can use to model how your correlation is matching the true system or something like that?
In terms of how the correlations match the true system, we don't have explicit data, okay? But we tested it for pretty much every possible correlation between -1 and +1. That's how we did it. In terms of the overall other structure, there are standard test problems available in operations research where, you make the cost between this, and this is how you generate the facilities, and a lot of the research papers have presented methodologies where you can generate standard instances which resemble industry settings. Yes, the correlation part, we did not have data. We knew it was correlated. The companies we talked with, freight companies are, they're a little bit reluctant to release their data, because they think that we'll share it with their competitors or whatever fears they have. So we couldn't, they said, yeah, there is correlation, we agree with you, but we won't give you what we have, sort of, So our way was just, okay, since correlation can only be between -1 and +1, let's just randomly generate all possible and then test it out. Okay.
More questions?
Thank you. Could you please go to the slide where you have the constraint on the problem?
Oh.
I think it's single sourcing constraint.
Okay.
Yeah. The second inequality, if I am right, is the constraint on the warehouses, YJK.
YJK, I think, should be between, warehouses and plants.
Shouldn't it be equality? The summation of all the IJK should be equal to 1, I think, because every warehouses should have a plan to provide products to it. And I think for your objective function is minimization.
Yeah.
So if you use inequality, so you can always use YJK equals to 0 to minimize your objective function.
Okay.
So if I am right.
Let me just think. I think VK is the facility location constraint where the plant is located. YJK is. So in this case, it is more of. Wait. In general, in the standard form, okay, in the standard form, yes, there definitely should be the equality, but again, I'm not able to exactly recall right now. We did transform the variables a little bit, because this YJK is actually, this VK corresponds to plant location, okay? And this YJK for warehouses, we had this one joint variable which does facility location and allocation, and that's one of the reasons why we wrote it like this. And I'm not exactly able to recall why we left it at a less than or equal to. Yeah, in the standard form, it should be equal to. Yes, I agree with you.
Thank you.
Thank you.
Other questions? Okay. I have a couple of questions.
Sure.
More on the application and also on the methodology. I can start with the easy one. I'd like to know how scalable is this method. I know you had a slide on scale or size of the problem being 1, 2, 3, 4. I'm not sure what that means exactly. How big of a problem are we able to solve?
We started with like 5 plant locations, 5 customer locations, 5 cross 5 cross 10, and then we went all the way up to, I think, 20 plant or 30 plant locations, 30 potential warehouse locations, and up to 100, 200 customers. Okay. I mean, yes, there will be a point where the nonlinearity just goes up like anything, and then I think pretty much any solution, then maybe we have to take a different approach. But I would say up to, when we tested up to 200 retailers, it still did fine, which was higher than what has been done in the literature. But my guess is after that, we'll have to maybe go on a heuristic route or something like that rather than relying on an algorithm, because I think then the nonlinearity becomes too high.
Right. Yeah. So a follow-up question, or the reason that I asked that question is that I see an immediate application in a subject which is very important in Minnesota. It's snow and ice removal.
Okay.
And I know DOTs are interested in locating truck stations in order to provide service, chemicals, and trucks to remove snow from the roads.
Okay.
And of course, we have the customers are the roads.
Okay.
That needs to be cleaned.
Okay.
And there is uncertainty in the amount of snow that you receive, and there is of course correlation.
Okay. Yeah.
And I'd like to know how scalable is this problem. The reason I asked that question was that it can be applied to that problem. I'd like to know your input on that.
Yeah, I mean, if you're looking at the customers as roads, right? I mean, and depending upon how you define a street, I would say, and looking at the correlations, and of course, when there is snowfall in Minneapolis, I mean, there's strong correlations.
Yeah.
If it's like 200, maybe 300 roads, depending on how you define the roadway stretches, I would say yes, go this route. After that, what happens is that the mixed integer nonlinear program you solve itself becomes very, very hard. I wouldn't trust the OA method to handle anything more than 300. Then maybe what we really need to do, but the good part about OA is that you don't need to solve the mixed integer linear program to optimality, and that's actually the direction we are working on right now. If you read Stephen Lever's dissertation, he actually shows that, and even in our case, when we tested it, where we, instead of solving the mixed integer subproblem to complete optimality, we cut it down at like 50% or 30%. We are still getting the optimal solution. So that would be, if we are going the OA route, that would be the direction I would take. Some intelligent way of solving the linear master problem, then which feeds into the subproblem, and that can help. Otherwise, yes, the formulation structure should be similar. Maybe we'll have to, solve small instances only using these optimization method and go to some taboo search or something like that. Other thing could be the way you abstract the road network, rather than you can choose this entire I-35 corridor as one road and Washington Street as other road. Those are the only two roads I know in Minnesota. So yeah, so you have these two and or like 10 to 12 street network. Then yeah, it will start falling into the limits of OA, and it should be a far more straightforward.
I guess the snow removal operation adds another level of complexity, which is vehicle routing, to how to route trucks to minimize the operation cost.
Yeah.
Besides that, I think there is something about 180 truck stations in the state of Minnesota, and DOT is interested in optimizing the location and operations.
Oh, okay.
But I guess there will be some
Definitely.
opportunity to collaborate.
Definitely, yeah.
I have some other question on the methodology, but I guess I can ask them offline. Thank you very much again.
Thank you. Thank you.
I'm going to ask first. Sure. I have 5 or 6 questions.